So now we're going to actually put ourselves in a place where we can calculate probabilities. And we're going to do that by introducing the so-called discrete probability law. Now, in order to do that, we just need to make absolutely clear that what we talked about in set theory really does have completely nice, completely clear parallels with the definitions we made regarding experiment. So that for every single definition we have there, there is a parallel in set theory. So let's just kind of put those down now. So when we kind of draw a Venn diagram, that's the best way to do it. So let's draw a Venn diagram with two sets, two potentially overlapping sets, and we'll have them A and B, and we'll have S. So the concept of the sample space, so let's talk about probability in this column, probability theory, and we'll have set theory in this list here. So here we're going to talk about the sample space. And in set theory, that kind of maps straight onto this notion here of a universal set. So this is the universal set, and the symbol is S. Perhaps you can guess why we chose the letter S to represent the universal set now. Not because it's a set, but because we mean to identify it with the sample space. And we want to draw that they're connected in this manner. Okay, so they're analogous to each other. Next, we're going to talk about outcomes. And all of the outcomes, the individual outcomes, are just elements of the sample space, right? But the sample space in set theory is the universal set. So all of the elements of the universal set. So each possible element of the universal set, each of those is an outcome, okay? Now we want to talk about how to build up subsets. So these sets here, these sets A, these are events. And of course, these are just subsets of the universal set. So, excuse me, universal. So A and B in this picture are events. Excuse me. There we go. Now, a trial is a single performance of an experiment. That's more kind of a conceptual notion, so there's no direct parallel with set theory there, but these actual objects, these things you can grab on, each of them, has something to do with sets. The sample space is just all the space available to us, the universal set. Each outcome is one possible point, one element that could be in, somewhere in the sample space. Maybe if I just kind of do this and then just label them and say each of these is an outcome. And A, of course, these, we understand, these are events. And we did some examples before, so we're not going to talk about that again. But now we're going to say, we're going to put ourselves in a particular situation. We're going to say, suppose I roll a die. So my experiment is that I roll a die. Well, looking at this, we're going to say, okay, let's draw the sample space. We're going to draw draw the sample space for this, and we're only going to identify 2 events, okay? And again, it's common practice with a Venn diagram to start with 2 events. You could of course always put as many as you like if you you can draw it, and under certain other constraints, but we won't get into that. But the point I'm trying to make here is let's identify the events A and B, and I'm going to say A is I roll an even, and B is I roll a multiple of 3. And I think you can see where these elements are going to go. The evens are, well, you start with 2, then you have 4. But you also have 6, which is both even and a multiple of 3. And next, you want multiples of 3, so you start with 3, but then you have 6, which you've already put in the intersection between those 2 events. So of course, really, we have a new event, A intersection B, which is I roll an even multiple of 3. Right, so these are my events here. So I've so far mentioned 3 events. I have event A, I roll an even. Event B, I roll a multiple of 3. And event A intersection B, I roll an even multiple of 3. Now I think you understand that I could really be more verbose, and I could say I roll an even, and I could say I roll an even and a multiple of 3, and a multiple of 3. But that's just to drive home the connection between the intersection and the word and. And now I'm going to say A union B. Well, A union B is I roll an even or a multiple of 3. So I can roll an even or a multiple of 3. So an even or a multiple of 3. And again, this is just to drive home this connection between this word or and the union. They kind of mean the same thing. Okay, so whenever grammatically you want to say or, you should think in terms of set theory of unions, and whenever grammatically you want to say and, you should think in terms of set theory of intersections. Okay, very good. So now, it's I think you kind of can see what these sets contain, but A is just 2, 4, 6. We're just reading it off. B is just 3, 6. A union B is just, everything. So 2, 3, 4, 6. And A intersection B contains just 6. So this is the only number that is both even and a multiple of 3 in this sample space. And of course, 2, 3, 4, and 6 are all the numbers that are either even or a multiple of 6, or a multiple of 3, excuse me. So again, what I've done here is I've kind of said a bunch of nothing about what I promised I'd say. So let's kind of get to that point. Here, we're trying to really think carefully about what we mean when we want to talk about we want to talk about probability. So how do we actually get the number? Well, I'm going to suggest just furnishing this list with one more list before we kind of go ahead, and that's the sample space itself. And the sample space itself, of course, contains 1, 2, 3, 4, 5, and 6. And they don't happen to be any numbers outside, of either A or B, but that doesn't matter. It's still the sample space. So it's everything in this outer bounding box. Okay. And of course, well, maybe I should put those numbers in, right? So you have a 1 that's not accounted for, and you have a 5 that's not accounted for. Okay. Very good. So now we're going to say, well, there's other things that we want to know. So for these sets, please just humor me for a second. We're going to think of counting how many elements are in each of those sets. Okay, and you might think, that's got to be important because we want to count chance, we want to count numbers, right? So a good place to start would be how many are in each set. I'm going to call the number of elements in A, I'm going to call that NA, and that's going to be 3. And I'm going to say NB is the number of elements in B. That's 2. Now we're going to write N, A union B is the number of elements in A union B. You can see there's 4 of them. The number of elements in A intersection B, well, that's just 1. And finally, the number of elements in the sample space, well, there are 6 of them because there are 6 results possible when you roll a die. Now, I don't think it should take too much to convince you that it's useful if I make this definition here. So I'm going to say, for a discrete sample space with a finite number of outcomes, the probability of an event A is given by this expression. We write PR of the event A, and we say that is equal to the number of elements in the event A divided by the number of events in the sample space. So we're asking what fraction of events in what is the fraction of events in A that are also in the sample space. So here, this is the fraction, outcomes, the fraction of outcomes in S that are also in A. Okay, so that seems utterly reasonable as a definition. So we'll maybe put that in a well, we don't need to put it in a box because we know it's a definition, but maybe it's worth just also enumerating what we mean here, because I know we kind of said before, but just for notes, it's worth saying where NA, we say, NA is the number of outcomes, I stress outcomes, in event A, and NS is the number of outcomes in the sample space. Okay, and here, let's just do some examples. Well, clearly the probability of our event A here has got to be 3 because there are 3 evens, and divided by 6 because there are 6 elements in the sample space, that's got to be a half. So there's a 50-50 chance of getting an even. So a 50-50 chance to get an even, And the probability of B is, well, B was the event we rolled a multiple of 3, and there are 2 multiples of 3 in the sample space, and there are 6 elements in the sample space in total. Well, that's clearly going to give us a third. So there is a 1/3, or let's say 33.3 recurring percent chance to get a multiple of 3. Because precisely 1/3 of these numbers is a multiple of 3. Very good. So now let's just do one more. So let's say the probability of A intersection B. So this is the probability of getting an even number that's also a multiple of 3. Well, we counted that set and there was one, oh, it was this one here, there's one object in it. And that's going to be 1, and there's 6 in the sample space, and that's our answer. We can't reduce that anymore. So what we would say here is there is a 1/6 chance to roll an even multiple of 3. Or like we did before, we could be a bit more verbose and say an even number and a multiple of 3, or an even that's also a multiple of 3. Okay. So this is the result, and we're going to make ruthless use of this result later on when we're kind of building up our probability models to analyze more interesting scenarios. But for now, it's worth just sitting on this and this example that we did just now.